Welcome to Networks Professionals.
Welcome to this explainer, where we're going to explore the epic rescue mission of the Internet's infrastructure and break down the incredibly intimidating architecture of our next-generation protocol. If you've ever wondered how the Internet manages to keep adding billions of smartphones, smart TVs, and IoT devices without completely running out of room, well, you are in the exact right place. Today, we're unpacking IPv6, and I promise you, by the end of this, you're going to understand exactly how the whole thing works.
Let's kick things off with a totally mind-boggling number. 3.4 times 10 to the 38th power. That represents roughly 340 undecillion addresses. Yeah, undecillion. This is the sheer mathematical scale of what our new hero protocol can generate to save us from a massive global connectivity crisis. To really put that into perspective, that's enough IP addresses to assign one to literally every single atom on the surface of the Earth, and we'd still have plenty left over. It's effectively infinite.
Section 1. The IPv4 address shortage. We are running out of space.
So you might be wondering, why on earth do we need a number that unimaginably large? Well, honestly, we've just completely exhausted the legacy IPv4 system. That older setup simply wasn't designed for a modern world where literally everyone has a smartphone, a smart TV, and, a connected fridge. Moving from a tapped-out 32-bit architecture, which could really only handle about 4.3 billion unique addresses, to this massive 128-bit system of IPv6 doesn't just double our capacity, it expands it exponentially to entirely future-proof the globe.
Section 2. Reading IPv6 addresses. Unmasking the format.
Let's break down an actual example of what this looks like. Unlike the old decimal dotted notation you're probably used to with IPv4, something like 192.168.1.1, IPv6 addresses are written out in hexadecimal. They're divided by colons into 8 distinct blocks, and each of those blocks contains 16 bits of information. I know, it looks less like a network address and more like a cat just walked across a keyboard. But engineers totally knew this would be a headache for us humans to read, so they built in some really clever tricks to make it readable.
Now here's where we get to play magician and make chunks of these cumbersome numbers just vanish, using 2 super simple abbreviation rules. First up, we've got leading zero suppression. If a block starts with zeros, you can just drop them. For instance, 0db8 just becomes db8. Simple, right? Second is the double colon rule. If you have a continuous string of entirely zero blocks, you can replace that whole chunk with a double colon. But there is a massive catch here. Just remember, the double colon can only be used once in any given address. If you used it twice, the computer wouldn't know exactly how many zero blocks were suppressed in each spot, and that would cause total ambiguity.
It's amazing how beautifully that long string reduces into something sleek and manageable. By simply dropping the leading zeros and squishing those empty blocks in the middle together with our double colon, what started as a daunting 32-character string becomes so much cleaner. It's actually highly logical once you know the rules, and it really is a breeze to decipher.
Section 3. The 64 by 64 architecture rule. Building the address.
So how do we actually organize all 128 bits of data to efficiently route traffic across the world without causing pure chaos? Well, it all comes down to a perfectly balanced 50-50 split. The address is cut exactly in half, 64 bits for the network ID and 64 bits for the interface ID. Think of this perfectly balanced split like routing mail. The first half, the network ID, gets your data to the right zip code and the right street. Once it finally arrives at the correct destination network, the second half, the interface ID, identifies the exact person inside the house.
Let's look a bit closer at that first half. The network ID is basically your global locator. It contains the global routing prefix and the subnet ID. This first 64-bit chunk acts as your neighborhood identifier. It's meticulously assigned by internet service providers and network administrators. Its entire job is to ensure that when a data packet leaves a server halfway across the world, the global internet routers know exactly which massive geographic network and local subnet to send it to.
And once that packet arrives at the local network, the second half takes over. The interface ID pinpoints your specific device. What's absolutely fascinating here is how this is generated. It can actually be cleverly auto-generated by the device itself using its own unique hardware MAC address through a process called EUI64. This means devices can literally configure themselves the moment they connect to a network. Or, alternatively, for those of us concerned about tracking, devices can just generate this ID randomly to protect your privacy.
Section 4. Major upgrades over IPv4. Fixing the old flaws. Now, IPv6 isn't just a bigger address book, it brings some actual superpowers to the table.
When the engineers redesigned the protocol, they took the opportunity to fix all the fundamental flaws of the old system. We're finally saying goodbye to outdated workarounds by baking mandatory upgrades directly into the core protocol. We're talking the elimination of NAT, built-in IPv6 security, the removal of network clogging broadcasts, and a much more streamlined header structure. Let's break these down real quick.
The most crucial point is that with infinite addresses, network address translation, or NAT, and port address translation, PAT, are completely obsolete. In the old days, NAT acted like a busy receptionist, taking one public phone number and hacking it to route to dozens of private extensions in your house. But in IPv6, every single device, your phone, your laptop, your smart thermostat, gets its own direct, globally routable line. Direct, end-to-end connectivity is finally restored.
Next up is security. In IPv4, security protocols were basically an add-on, kind of an afterthought. But with IPv6, Internet Protocol Security, or IPsec, is baked right into the core protocol. This means end-to-end data encryption is a foundational element. You no longer have to bolt security on hoping it holds. It's a built-in requirement for every single connection, making the next-generation internet vastly more secure right out of the box.
Then we have network efficiency. If you've ever managed an IPv4 network, you know exactly how terrible broadcast traffic is. When a device wants to find something, it literally screams its request to every single device on the network, wasting huge amounts of processing power. IPv6 entirely replaces these notoriously heavy broadcast messages with targeted multicast. That means packets are efficiently sent only to the specific group of devices that are actually subscribed to hear them, so no more shouting in a crowded room.
And finally, we have the simplified fixed 40-byte header. By shedding all that old baggage, the optional fields and redundant checksums, IPv6 completely streamlines the data packets. Routers just don't have to think as hard or process as much metadata just to pass a packet along. This allows our global infrastructure to process data packets at literal lightning speed.
Section 5. Transitioning to IPv6 networks. Bridging the gap. Okay, so this all sounds absolutely incredible, right? But there is a catch. Because IPv6 is essentially an entirely new language, it is not backwards compatible with IPv4. We can't just flip a switch overnight and turn off the old internet. So network administrators use a specific progression of tools to ensure the old internet can still talk to the new internet. These transitional mechanisms fall into three main strategies: dual stack, tunneling, and translation. Here's exactly how they work. With dual stack, devices basically become bilingual. They run both the IPv4 and IPv6 stacks simultaneously so they can talk to either network natively. If two IPv6 networks are separated by an older IPv4 infrastructure, we use tunneling to literally encapsulate the new IPv6 packets inside old IPv4 envelopes to sneak them across the legacy gap. And finally, when an IPv6-only device desperately needs to talk to a legacy IPv4 server, we use NAT64, which acts as a real-time translator, perfectly converting the traffic back and forth.
The sheer engineering required to keep the entire internet running while simultaneously upgrading its very foundation is nothing short of incredible. As we finally leave the constraints of the 32-bit era in the dust, we're entering a world of unhindered connectivity. No more address shortages, mandatory high-level security, and beautifully streamlined routing. It's fascinating to imagine the massive network expansions these 340 undecillion addresses are going to unlock. So the real question is, with a boundless canvas of infinite addresses and ultimate security at your disposal, what will you build on IPv6?
Thanks for watching.